Welcome to Pre-Calculus. In this video, we're going to start looking at section 10.8. We've been working with polar coordinates, and now we're going to see what those graphs look like of polar functions. Today, we'll look at the first bullet point, polar equations by plot pointing. We'll talk a little bit about symmetry, but more on that in the next video. And in the third video, the special polar graphs. So, what we got here, we've sketched graphs in the rectangular system before. We begin with a basic point plotting method. Then you use sketching aids such as symmetry, intercepts, asymptotes, periods, and shifts to further investigate the graphs. Blah, blah, blah. Let's see what we got here. It says, sketch the graph of the polar equation of r equals 4 times sine theta. The sine function is periodic, so to obtain a full range of r values, consider the values of theta on one trip around the unit circle from 0 to 2 pi. So I'm going to write down here, our r value is going to be 4 over 1, times the sine of some angle theta. And let's do a few of these. Here's our angle 0. The sine of 0 is 0. 4 times that is 0. Now, if I put a pi over 6 in here, the sine of pi over 6 is 1/2. So we're going to have 4 times a half. That's 2. Now, if we plug in a pi over 3, then we'll have 4 over 1. The sine at pi over 3 is root 3 over 2. This 4 divides by that 2, so that'll be 2 times the root of 3. Now to sketch a graph, though, I would prefer a decimal, and 1 decimal point is fine. That's about 3.3. Let's see, sine of pi over 2. The sine at pi over 2 is 1. So 4 times 1 is 4. Now 2/3 pi. The sine at 2/3 pi is a positive root 3 over 2. So that is also going to turn out to be 2 roots 3, exactly like this pi third. It's also going to be the decimal 3.3. If we go to 5 pi over 6, sine of 5 pi 6 is the sine of pi 6. It's a half, so a half times 4. This number is also 2. If we plug in pi, the sine of pi is 0. 0 times 4 is 0. So it looks like here we went from 0, our numbers got up to 4, and then they come back down to 0. This might be one full cycle. But let's keep going. I'm going to switch my ink color to red. If we do 7 pi 6, the sine of 7 pi over 6 is negative a half. Negative a half times 4 is negative 2. Now, we're not doing every angle over here, but here's another one. 3 pi over 2, the sine value there is negative 1, times positive 4 is negative 4. 11 pi 6 and 7 pi 6 have the same sine value, negative a half, so we'll get the same output at negative 2. The sine of 2 pi is the same as the sine of 0, and the sine of pi, 0. So we've got some points here, and let's hop over to a graph and start plotting those points. Oops. Yeah, and we're only going to need this upper half here. Let me make it a little bit bigger. So our first point was 0, 0. We begin at the origin. And then we had pi 6. Here's the ray for pi 6. And at pi 6, we went out 2 units. 1, 2. So if we start connecting the graph, it's going to look a little something like this. And then we put in pi over 3, and we got the decimal about 3.3. Oops. So 1, 2, 3, and I'm going to estimate about 1/3. So it looks like our graph is going to continue like that. At 5 pi over 6, oops, I think I missed one in there. 2/3. Oh, pi over 2, oops, we did that one, that one, that one. At pi over 2, we go out 4 units. So we're going to go straight up 1, 2, 3, 4 units. This is a pretty terrible graph, but it's coming around there. What did we have next? 2/3 and 3.3. So here's 2/3 pi, 1, 2, 3, 0.3. The graph is coming back around. Next, 5 pi 6, 2 units. So here's our 5 pi 6. We go out 1, 2. The graph is coming back around. And then at pi, we're back to 0. So it looks like, if my graphing skills were a little better, that should be a circle. Let's keep going. Oops, wrong way. 7 pi over 6, it's now negative 2. Oops. So if we come down here to 7 pi 6, we would go negative, which is going to shoot us back this way, 1, 2. So yeah, that dot landed right on top of that one. At 3 halves pi, we would have negative 4. 3 halves pi is straight down, so the negative would shoot us across, and we wind up here. Yeah, so it looks like we have overlap. 11 pi over 6 is negative 2. 11 pi 6 would be down here, and if we go negative 2, 1, 2. So yes, we did find one full cycle here. We went from 0, got to our max value, and then back to 0. And again, this graph, 4 sine theta, is a circle that goes through the origin, and it has a diameter of 4. 1, 2, 3, 4. So the center of this circle would be at this point right here in the middle, on the 90-degree axis, the pi over 2 axis, at 2 units from the origin. And we can sort of say from this, if we have something that looks like this, 4 sine theta, we do have y-axis symmetry. In polar coordinates, we call that symmetry to pi over 2. Pi over 2 is the positive y-axis. You know, if we had known that at the start, as soon as I found this point, I could have graphed this point. As soon as I found this one, we could jump across the y-axis and hop over to that other point. So that was 4 sine theta. Here's a practice problem for you. 6 cos of theta. So pause the video, fill in the chart, and try to graph that function. All right, let's see how well you did. At 0, you should have got an output of 6. The next one, pi 6, should have been 3 root 3, or about 5.2. Pi over 3, the cos is a half. Half times 6 is 3. And if we think back to when we graphed these, again, this was 6 cos theta. Where is cosine equal to 0? Cosine is equal to 0 at the top of the unit circle at pi over 2. I know that's going to be a 0. And also at 3 pi over 2. So we can plug in that right now. At 2/3, you should have got a negative 3. At 5 pi over 6, a negative 5.2. Here's our positive 5.2. At pi, you should have got negative 6. 7 pi over 6 is negative 5.2 also. 11 pi over 6, we're back to a positive 5.2. And 2 pi is just the same as 0. We're back to a 6. So our first point at 0, on the 0 radian array right there, we would be out 6 units. 1, 2, 3, 4, 5, 6. At pi 6, we're going to go out 5.2. 1, 2, 3, 4, 5, and just a little bit past that. At pi over 3, it's a nice even 3 units right here. At pi 2, we are at the origin. And then if we go to 2/3 pi, we would go negative 3. Well, here's 2/3 pi. Negative will shoot us across. 1, 2, 3. At 5 pi over 6, it's negative 5.2. Here's 5 pi 6, or negative 5.2. So 1, 2, 3, 4, 5, and 0.2. And then at 3 halves pi, we're back to 0. So it looks like we have a circle here. If these points will just be a little overlap. 11 pi over 6, 5.2. Well, here's 11 pi over 6. We have our 5.2 already. And at 2 pi positive 6, that was our first point here. So this looks like a circle. It has the diameter of 6 because it was 6 cos theta. And we are on the x-axis, and we go out from the origin. Our diameter would take us out to 6. So that would put our center right on the 0 radian positive x-axis, right here 3 units from the origin. If I recap here real quick, when we did the sine, we did have y-axis symmetry. So we could have jumped across when we found those points in the first quadrant. Here we can see that cosine has symmetry to the x-axis. When we found this point, we have a symmetric point straight across. When we found this point, again, the symmetry could have given us the point on the other side of the x-axis. All right, let's try one more example. Here's some stuff about symmetry, zeros, and maximum values of our function. They got the absolute value bars around the r radius. Note in example 1 that as theta increases from 0 to 2 pi, the graph of 4 sine theta is traced twice. Moreover, note that the graph is symmetric with respect to the line theta is pi 2, or the positive y-axis. Had you known this about the symmetry and retracing ahead of time, you could have used fewer points. The figures below show 3 important types of symmetry to consider when sketching polar curves. So the first one we saw in example 1, symmetry with respect to the line pi over 2. They do it this way. Our trig function with theta in it would be the same as with if we change our r to negative and our theta to negative. Symmetric about the polar axis or the positive x-axis. We saw that in the practice problem here. R negative theta is the same as negative r pi minus theta. And then we could have symmetry to the pole. Remember, the origin is the pole, so we would jump straight across the pole. So let's see here. These are our tests. I don't use these all this often. I don't mind just plotting more points just to make sure. We're symmetric to the line theta is pi over 2. If we replace our r theta with r theta minus pi, or pi minus theta, or negative r negative theta. The polar axis or the x-axis, we could replace r theta with r negative theta, or negative r pi minus theta. Or to the origin or the pole, we could replace r theta with r pi plus theta, or negative r, keep the positive theta. So let's take a look here at example 2. Our function is 3 plus 2 cos theta. We saw in example 1, or the practice problem, that we are going to be symmetric to the polar axis. Symmetric to polar axis, or remember that's the x-axis. So as we graph each of these points, we'll graph them one at a time, and then we'll hop across the x-axis to graph the symmetric point. So let's do a few values here. We're going to plug our angles into 3 plus 2 times cos theta. The cos at 1, or 0 radians, cos is 1, so that'll be 1 times 2, that's 2, plus 3 is 5. And let me write this again, 3 plus 2 times whatever our cos value is. If I plug in pi over 6, the cos value there is root 3 over 2, so the 2's cancel, and we get 3 plus the root of 3. And 3 plus root of 3 is about 4.7. Ooh, I forgot, let's graph these as we go. Our first one, 0 radians, 5 units. Here's 0 radians, 1, hold on, we'll just do that all at once. I see I already have the table filled in over there. At pi 3, our cosine value is a half, so we'll have a half of 2, that's 1, plus 3 is 4. At pi over 2, cos is 0, so that's 0 times 2 plus 3 is 3. 2/3 pi, the cos at 2/3 pi is negative a half. So this becomes 3 minus the root of 2, or about 1.6. Oop, I didn't plug in. At 2/3 pi, yeah, I didn't put my 2 in there. At 5 pi over 6, the cos value is negative root 3 over 2. So this becomes the 3 minus root 2, or about 1.6. If I plug in pi, cos of pi is negative 1. So negative 1 times this 2 is negative 2. 3 minus 2 is 1. Okay, we've got some points in here from 0 to pi. Now let's graph them and do their reflective points. So here they are. I need my decimals there. That's about 4.7. This is about 1.6. So at 0, we're going to go out 5 units. 1, 2, 3, 4, 5. We are on the axis that we are symmetric to, so that's our only point. At pi 6, we go out 4.7. 1, 2, 3, 4. 0.7 would be about here. And now we can go across, straight down across the x-axis, and there's our symmetric point. Next up, pi 3, we go 4 units. 1, 2, 3, 4. And then from there, we are going to look straight down. And it looks like we're going to hit right here. Oops. Yeah, right there. Oh. Next point, we did the pi 3, 4. Pi 2, comma 3. So we're going to go straight up 1, 2, 3 units. That means our reflective point would be straight down 1, 2, 3 units. Oop, I wanted to use red there. There we go. At 2/3 pi, it's 2 units. So 2/3 pi is right here. We'll go 1, 2 units. And then the symmetry means we'll go straight down here. There we go. And then at pi, we're going to go out 1 unit. So 1 unit out there. And again, we are on the x-axis. So there would be no sort of symmetric point to that. Oop, did I miss my 5 pi over 6, 1.6? Yeah, 5 pi over 6, 1, and 0.6 is a little more than half. So we would have to go straight down, and we're right there. Oops, I'm not on the line. There we go. All right, let's connect the dots, see what it looks like. Started here at 0, 5, and then we come up, and we curve, and we start heading down this way. Oops. Like that, and then we come in here, and then if we do the symmetric of that, it's going to look a little like this. So it's kind of like a circle, but we got a little dimple here. All right, symmetry to sketch the graph. Again, when we started here, it was cos, so we had symmetry to the x-axis. I'll give you a clue on the practice one. This is sine, so you're going to have y-axis symmetry. So pause the video and give it a try. Oops, now I just looked in my notes, and I do have, your notes should be good, but I don't have them clipped here in the video. I'm going to change these angles to the one that'll match your notes. Okay, so here's our output values, our R values, the radius or our distance from the origin. For the given inputs, our given thetas. And let's put some of these points together. Okay. Oops. So at 3/2 pi, we're positive 1. 3/2 pi is straight down, so that's positive 1. At 5, and we have, in this case, again, we're going to be symmetric to the y-axis. We are on the y-axis, so there is no symmetry to that point. At 5/3 pi, it was 1.3. Here is 5/3 pi. 1 1/3 would put us about there. And then our well, let's do all the points, and then we'll do the symmetric points across. At 11 pi over 6, it was positive 2. Here's 11 pi 6. We'll go out positive 2. Next was 0, 3. So 0, 1, 2, 3 right there. Next up was pi 6, 4. 1, 2, 3, 4. At pi 3, it was 4.7, 1, 2, 3, 4, and almost to the edge there. And then we had, that was pi, pi over 2, 5, 1, 2, 3, 4, 5. So there are the points from our table, and we should be able to go straight across. Like I'm going to come straight across here and put down the next point. And then here we're going to come straight across, and that'll be right there. Here we are on the positive x-axis or the polar axis. We're going to go to -3. This little point will come over right here. And finally this one to right here. Okay, so I'm going to do this side first. We started here at negative pi 2 or 3/2. And our graph comes around like that. And then the stuff on the other side of our y-axis. Oop, I missed that one, but you'll be all right. There we go. Again, kind of a circle, but we got a little dimple here on this side. Okay, I think that's enough for this video. Let's check this out. Example 2 uses the property of cosine function being even. Think way back to section 4.2 when we did the unit circle, that cosine function is even because the cos of a negative angle is the same as the cos of that same positive angle. And the sine is odd because sine of a negative angle is the same as the negative sine of the same angle but positive. The test for symmetry and polar coordinates listed on the preceding page are sufficient to guarantee symmetry, but the graph may have symmetry even though the equation does not satisfy the test. Blah, 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 blah. Yeah, again, getting into this, I think that's a little bit much. Again, if you're worried, just graph a few extra points. All right, in class, we'll do some practice problems, and I'll see you then.